On the night of April 23rd into April 24th, 1945, a single heavy bomber over Norway began as a clandestine Special Operations Executive SOE supply drop to resistance forces behind German lines and ended as a terminal salvage scenario. The aircraft was a Handley Page Halifax A Mark 7, serial number NA337, flying with RAF Squadron 644. It took off at 1951 hours and by about 01:45 was taking fire over Lake Mjøsa. The flight plan required low-altitude navigation through defended airspace, a profile that removed the safety margin provided by height. The structural integrity of the aircraft was compromised near the Minnesund railway bridge. Ground positions engaged the bomber with 20mm flak. One shell struck the starboard wing, penetrating the fuel tank and igniting a fire. In aviation forensics, a wing fire creates a strict time horizon. The heat weakens the aluminum alloy spars that carry the lift load. If the fire burns long enough, the wing separates and control is lost completely. For Flight Lieutenant Alexander Turnbull, the wing fire turned the decision into a countdown. He could order a bailout, scattering the crew over freezing water and hostile territory, or he could attempt a controlled ditching on the surface of Lake Mjøsa. Turnbull selected the ditching option. This procedure requires bringing a 20-ton aircraft down onto a fluid surface at nearly 100 miles per hour. The physics of ditching a heavy bomber involve managing the deceleration vector. If the nose digs in, the aircraft flips and breaks apart instantly. If the descent rate is too high, the fuselage creates a hydraulic hammer effect upon contact. The Halifax hit the water in a nose-up attitude. The initial impact was survivable, but the deceleration forces exceeded the structural limits of the rear fuselage. The ditching tore the tail section away. This structural failure created the only viable exit route for the crew in the rear. Flight Sergeant Thomas Weightman, the rear gunner, was thrown into the lake as the Halifax broke apart. In the darkness, he fought to free the crew dinghy by hand. The main fuselage, with the other 5 crewmen and the burning starboard wing, began to settle as water flooded in. It pitched forward and began the transit to the lakebed. The tail section remained afloat just long enough for Weightman to escape before it too slipped beneath the surface. He was the only survivor of the 6-man crew. 5 of his crewmates did not return. The wreckage of NA337 settled on the bottom of Lake Mjøsa at a depth of 750 feet. This depth places the aircraft far beyond the reach of casual diver interaction or surface weather effects. At 750 feet, the external pressure is roughly 330 pounds per square inch. The environment is dark, silent, and thermally stable. For decades, the location served as a marker of the loss. 4 of the fallen were recovered from the lake the next day. 1 man was never found. The recovery of this airframe presents a different problem than shallow water salvage. In the shallows, wave action, oxygen-rich currents, and human interference grind wrecks down to fragments. Here, cold freshwater slowed that usual erasure to a near standstill, leaving NA337 almost frozen in time. But the same depth that protected it also locked it away from standard recovery methods. At this depth, every move becomes a structural load case. The aircraft was designed to bear aerodynamic loads in the air and compression loads on its landing gear. It was not designed to be hoisted by its airframe while filled with tons of water. The static geometry of the wreck on the lakebed suggested that the aircraft was upright, but the extent of the damage from the flak and the impact remained obscured by the silt. The separation of the tail section during the crash provided the first clue to the structural state of the bomber. It indicated that the fuselage had already failed at a critical junction. Any attempt to lift the main body would need to account for this breach in continuity. The objective was to recover the fuselage and the wings as a single unit, a requirement that imposed severe constraints on the lifting gear. A standard crane line attached to the spar would simply tear the wings off the fuselage due to the weight of the water trapped inside. For 5 decades, the Halifax remained a verified loss, but an unverified target. The technology required to locate, survey, and lift the machine without destroying it did not exist in 1945. The transition from a crash site to a recovery site would require a new set of tools and a rigid adherence to the physics of deep water lifting. The lake held the evidence of the 24th of April, but it would not release it easily. Inside the Halifax, a crew coffee thermos survived the decades underwater. After the recovery, it was found among the aircraft's fittings and later returned to Flight Sergeant Thomas Weightman. The object does not prove the crash was gentle. The airframe still broke apart on impact, but it does show how the lake preserved small, human-scale details once the wreck came to rest. From that point forward, Lake Mjøsa became less a hazard than a cold storage vault. In the deep, lightless water of Lake Mjøsa, temperature holds at about 4 degrees Celsius. The airframe became cold-soaked for decades, minimizing thermal cycling, and the freshwater environment slowed corrosion to a crawl. Instead of being chewed apart like many saltwater wrecks, the Halifax endured, remarkably intact for its age. However, the depth imposes a severe physical load on the airframe through hydrostatic pressure. This is the force exerted by the weight of the water column above the object. At this depth, hydrostatic pressure loads every panel with crushing force. While the Halifax is open to the water, allowing the pressure to equalize inside and out, the force ensures that no air pockets remain. The structure is completely flooded. This saturation creates a critical constraint for any future recovery. The aircraft is no longer just aluminum and steel. It is a vessel containing tons of displacement water that has become part of its resting mass. Understanding the state of the wreck means replaying the moment the lake took it. In a ditching, there is no landing gear to bleed off the hit. The Halifax had only skin and momentum. When the water arrested the cabin, the aft structure kept driving forward, loading the fuselage joint in pure shear until the riveted frame gave way. That break did not make survival inevitable, but it created a brief window. The Halifax came down hard, the nose and tail were torn, and the aircraft stayed afloat only for a short time. Several men got clear of the wreck, but the lake was near freezing, and without a functioning dinghy, they succumbed to hypothermia. In the rear position, Flight Sergeant Thomas Weightman managed to manually release the dinghy, clung to it in the dark, and was later pulled from the water alive. Only Weightman was still alive when rescue arrived. The result of these lost mechanics is a paradox. The cold, fresh water has preserved the aluminum skin in a condition rarely seen in aviation archaeology. The paint is intact, the nose art is visible. But the structure is broken. The airframe is split in two, and the main section is filled with water that adds tons of dead weight to the assembly. The environment saved the materials, but the impact destroyed the structural continuity required to lift it. The evidence is pristine, but it is trapped in a fragile envelope that cannot support its own recovery without external reinforcement. In 1991, the search shifted from paper records to the lake itself, and the aircraft was located on the bottom of Lake Mjøsa. In 1995, the effort moved from investigation to recovery. At that depth, the site was off-limits to conventional diving, so the team relied on a remote-operated vehicle, or ROV, to survey the wreck and guide equipment in the dark. The ROV inspection revealed a condition that defied standard marine salvage expectations. In most underwater crash sites, the aluminum skin of the aircraft is heavily degraded. This is typically caused by galvanic corrosion. When aluminum and steel components are submerged in salt water, the water acts as an electrolyte. This creates a battery effect where electrons flow from the aluminum anode to the steel cathode, dissolving the aluminum in the process. However, Lake Mjøsa is a freshwater environment. The water lacks the conductivity to support this aggressive electron flow. The circuit is effectively broken. Furthermore, the wreck was partially covered in a fine layer of silt. In places, that sediment can limit water movement and reduce oxygen contact at the metal surface, slowing corrosion and biological growth. It is a protective microenvironment, not a guarantee of a fully oxygen-free site. The ROV lights revealed paint that still held its color and structural panels that appeared factory fresh. The Halifax sat upright, apparently intact except for the missing tail. This visual confirmation presented a deceptive data point. The aircraft looked robust, but appearances at depth are not indicators of structural strength under load. The airframe is held together by thousands of rivets. While the skin was bright, the condition of the internal steel spars and bolts remained unknown. The survey confirmed the identity of NA337, but it also confirmed the scale of the logistical problem. One common way to reduce risk is to recover a wreck in sections. In this case, the team decided to raise the Halifax with its wings still attached, aiming to preserve the aircraft as a single historical artifact for museum display. That choice removed the simplest option and forced the engineering plan to change. By refusing to cut the wings, the team accepted a massive increase in difficulty. Instead of lifting a compact fuselage cylinder, they now had to lift an object with a wingspan of over 100 feet. This created a giant surface area that would act as a water break during the lift. The wings would trap water, increasing the effective weight of the load. If the lift speed was too high, the drag on the wings could rip them off the fuselage at the root. If the lift was too slow, the unpredictable currents in the water column could rotate the aircraft, twisting the frame. The survey proved the Halifax was worth saving, and now every shortcut was gone. The existing tools of the salvage trade were insufficient for the task. One straight pull from above and it would come up as scrap. The team required a method to support the entire surface area of the aircraft from below, essentially building a dry dock under the water. The solution would not be found in a catalog. It had to be fabricated from scratch. To retrieve the Halifax without destroying it, the recovery team had to invert the structural logic of the aircraft. A bomber is designed to be supported by the lift generated by its wings or by the compression of its landing gear. It is not designed to be suspended from a hook. If a standard salvage sling is wrapped around the fuselage, the crushing force of the cable will buckle the aluminum skin the moment tension is applied. Once the skin buckles, the structural continuity of the airframe fails, and the fuselage will snap under its own weight. That continuity is the whole game. Skin and stringers acting as one. Crush the skin and the tube fails. So the Halifax could not be lifted from above. It had to be carried from below. The solution was a custom-built steel lifting frame, a cradle made to support the aircraft from below. Guided into position with an ROV, the frame was worked under the wings, so the lift could be carried at the wing roots and main spars, the strongest parts of the structure, without crushing the thin fuselage skin. The deployment of this cradle at 750 feet required a complex choreography between the surface crane and the subsurface ROV. The pilots had to lower the 2,500-pound steel frame through the darkness and thread it around an aircraft with a wingspan of 100 feet. There was no margin for collision. A heavy steel beam swinging into the preserved aluminum would cause catastrophic damage. Once the cradle was positioned under the wings, the crane began to take up the tension. As the assembly began its ascent, the operation entered a zone governed by dynamic loading. In a static environment, the weight of the load is constant. In a fluid environment, the effective weight changes based on velocity. As the aircraft moves up, the water resists the motion. This drag force is added to the static weight on the crane cable. If the crane operator lifts too fast or if the surface barge heaves in a swell, the drag spikes. This spike can overload the old aluminum spars or the lifting rig itself. The lift had to be executed at a crawl to keep these dynamic forces within a survivable envelope. The most critical phase of the recovery occurred at the interface between the water and the air. This boundary is known as the surface tension break. When an object is fully submerged, the water provides buoyancy that supports some of its mass. As the aircraft breaches the surface, it loses that buoyant support instantly. Gravity reasserts its full force on the exposed section, while the submerged section is still being pushed up by the water. This creates a massive differential stress across the airframe. For the Halifax, the risk was magnified by the water it carried inside. As the aircraft breached the surface, buoyant support fell away, but the flooded interior could not shed weight instantly through the drain holes. If the crane lifted the fuselage faster than that water could escape, the trapped load could tear floors and fittings apart. The team managed the break inch by inch, raise, pause, let it drain, until the inside and outside could equalize without the airframe giving way. From here on, the lift was governed by mass, not depth. As buoyancy fell away, trapped water tried to stay with the airframe, and the cradle load could spike without warning. The only safe move was patience. Raise, pause, let it drain, then raise again. This phase required a disciplined pause at the surface. The team used high-capacity salvage pumps to actively dewater the fuselage while it hung suspended in the cradle. They were not just lightening the crane's load, they were preventing the internal flood from shearing the floor rivets and tearing the belly open. The floor was built for men and cargo, not a suspended column of water. Once the water level inside equalized with the exterior air, the operation pivoted to the shore transfer. This presented a new constraint: ground pressure. The recovery site at the edge of Lake Mjøsa was a natural shoreline composed of soft sediment and soil. It was not an industrial port. The logistics required a heavy mobile crane and a flatbed transporter to receive the aircraft. The combined weight of the recovery machinery and the bomber would exert a pressure per square inch that exceeded the bearing capacity of the ground. If the wheels of the crane sank into the soft earth while holding the suspended load, the center of gravity would shift. A shifted center of gravity during a lift can cause a crane to tip over or the load to swing uncontrollably. The dynamic loading on the airframe during such a swing would shatter the brittle aluminum components that had survived decades underwater. To prevent this, the recovery team had to engineer a temporary hardstand. The solution involved a massive logistical intervention. The team ordered 20 truckloads of crushed rock to be delivered to the site. This material was graded and compacted to form a reinforced causeway extending from the road to the water's edge. This layer of rock distributed the weight of the heavy machinery over a wider surface area, reducing the ground pressure to a safe level. It converted a soft, unpredictable beach into a stable, industrial platform capable of supporting the transfer. The final maneuver involved swinging the 18-foot high cradle onto the waiting transporter. This was the moment where the custom engineering of the lifting device proved its value. The cradle was not just a hook, it was a sled. It provided a rigid exoskeleton that protected the aircraft during the handling process. The wings remained supported by the steel frame, preventing the sagging that would occur if the aircraft were placed directly on blocks. With the Halifax secured on the transporter, the immediate physical risk of the lift was resolved. The aircraft was no longer a shipwreck, it was a recovered artifact. However, the removal of the water introduced a new chemical threat. For 5 decades, the cold, oxygen-depleted environment had paused the corrosion process. Now, exposed to the oxygen-rich atmosphere, the aluminum was vulnerable to rapid oxidation. The aircraft was on dry land, but it was not yet safe. The clock had restarted, and the mission parameters shifted from salvage to conservation. The recovery of Halifax NA337 was not merely a salvage operation, it was the retrieval of a unique dataset from the bottom of Lake Mjøsa. Following the successful extraction in 1995, the aircraft was disassembled for transport. The components were loaded onto flatbeds and shipped across the Atlantic to the National Air Force Museum of Canada in Trenton, Ontario. It was no longer a shipwreck, it was evidence ready to be read. The subsequent restoration process served as the final validation of the engineering decisions made on the lake. Kjarsgaard refused to let the wings be cut free, and the payoff came later. The restoration team received a continuous structural skeleton. Wing roots stayed true to their original geometry, and no cut spars had to be rebuilt from scratch. The integrity of the airframe allowed the museum to rebuild the aircraft around its original engineering geometry. The result is an anomaly in the world of aviation preservation. Halifax NA337 is the only fully restored Handley Page Halifax on public display. Other Halifax airframes survive only as partial relics or reconstructions, which makes this recovery a rare correction to the historical record. It allows historians and engineers to examine the construction techniques and material choices of the Handley Page design team as they existed in 1945. The quality of the artifact is a direct consequence of the deep water environment. The absence of galvanic corrosion and the thermal stability of the lake meant that the percentage of original material in the restored aircraft is exceptionally high. The skin panels, rivets, and internal stringers are the same components that flew the mission. This level of preservation permitted a detailed forensic verification of the loss. The starboard wing still bore damage consistent with the documented account of a 20mm flak strike near the Minnesund bridge. The project also resolved the human questions surrounding the crash. Flight Sergeant Thomas Weightman, the rear gunner who escaped the sinking tail section, lived to witness the recovery of his station 50 years later. The coffee thermos found in the rear turret was returned to him, a tangible proof of his presence and survival. For the families of the 6 crew members who did not escape, the aircraft serves as a permanent memorial. It is no longer a missing number on a squadron roster, it is a physical presence that acknowledges their service. The legacy of the operation lies in its proof of concept. The team demonstrated that deep water recovery is feasible without destroying the integrity of the target. By prioritizing the physics of the lift over the speed of the extraction, they successfully reversed the trajectory of the loss. NA337 was pulled from the cold storage of the lakebed and restored to the public trust. It stands today as the cost made physical, Squadron 644 in the final days of the war, measured in aluminum and lives.